All right, problem number 14. So look at all these. They put the physics teacher staying on a scale in a lift. And then they put elevator in parentheses as a conciliatory bone to us Americans. Um, you know what? Whatever. They don't love America like I love America. Okay, so the elevator is moving steadily downwards at a speed of 3 meters per second. Ooh, want to highlight some things as I read this. When we move down at a steady speed, the net force is 0, and what that means is the reaction force and the weight force are going to totally balance. And by the way, one other thing is whenever you have scales on an elevator, I want to be clear, this is the normal reaction force. This is also what the scale says. So let's be careful on that. Now, we've got the free body diagram of moving down at a constant speed, so let's go ahead and label what we have here. So we're going to have the reaction force going up and the gravity force or the weight force going down. Now, if the elevator is slowing to a stop, let's be clear. The weight force wants to drive the elevator down into the earth. And if we're going to slow it to a stop, we need, and if we want to slow the person on the scale to a stop, that means the scale has to push up on them with extra force in order to slow them down. I would even here label, okay, this. I don't know if the IB does this. I don't think they do, but I want to be really clear in my picture that I'm trying to indicate that. All right. Now here. The reading on the scale for the constant velocity stage, let's see what we have. Well, we know that for the first part, we said that r equals fg because they're balanced, because it's not accelerating. So that's mg, so that's going to be 60 times 10, which is going to be a 600 Newton force, which is fine. All right, now in the slowing stage, let's remember the forces are not balanced. Let's just redraw that free body diagram. We got r, we got fg, and let's be clear, we have r going up, fg going down, and the effect is that the elevator accelerates. So we know that r here, it's going to be really tempting. Please, okay, do not put 600 newtons in there for r. You actually have to calculate a new force for r because r actually increases as the elevator stops. So let's put in what we do know. We have r as an unknown. Fg, now that is 600 newtons, which we got from before because the weight doesn't change, times 60 times the acceleration of the elevator. So we have to get the acceleration of the elevator based on the data. Of course, I'm going to grab a data booklet equation, v equals at plus u. And let's put in the numbers that we have. So it takes 2 seconds to come to rest from 3 meters per second. So we go ahead and we'll put in those numbers. So we have 0 equals a times 2 plus 3. And here we're going to end up getting a is, you know, this is what I don't like about the IB and our calculations here. So a is negative 1.5 meters per second squared. Now, what I'm going to do is I'm going to use the absolute value in here. Let me explain why. So we said that the acceleration here of gravity is negative. So we need to flip the sign convention here. A is plus 1.5. So we need plus 1.5 because we already said that down is negative, but this 1.5 is upwards. So when I plug it into here, I'm going to plug in plus 1.5. So using all of that data, we're going to say r minus 600 equals 60 times 1.5. So the slowing stage scale reading, which is the same as the normal force, is going to be 690 newtons. And for part 2, we'll take a look at that. So, a girl and a boy on a bicycle, it's so cute. The boy wishes to get off the back of the bicycle while it's still moving. He knows that if he just puts his feet on the ground and stands up, he's likely to fall over. Why is this so? So there is actually a real reason for this. and it is based on the first of Newton's laws. So it turns out his feet stop on the ground, but because his body is moving, it will keep moving because of Newton's first law. And he will fall over. All right. And for part B, it says, so he pushes himself off the back of the bicycle by pushing forward in the bicycle frame with his hands. He lands on the ground with 0 horizontal velocity. And we want to calculate the velocity of the girl on the bike immediately after. So let's be clear, this is clearly a momentum problem. Let's just say this. Let's take the total mass times v times u, the original speed, equals the mass of the bike and the mass of the girl plus the mass of the boy times 0. So what this means is we have a total mass of 40 plus 30 plus 10, which is 80, going at a speed of 2.5 equals mass of just the bike and the girl. That's going to be 50 times its v that we're solving for plus 0. So we're going to end up getting 120 equals 50 v. This cancels. 12 divided by 5. That does not make sense. 80 times 2.5. I'm so sorry. 80 times 2.5 is 160 plus 40, which is 200. So this is 20 equals 5v, so 20 divided by 5. We're getting v equal to 4 meters per second in part B. And then we want the kinetic energy before and after. I'm going to actually let you figure this one out, but the kinetic energy before is going to be 1/2 m total times v squared, and the Ke after is going to be 1/2 mass of the girl plus mass of the bike times v after squared. And here you'll put in 2.5, and here you're going to put in 4. Okay. And of course, as always, there's an increase in Ke because the boy turns chemical energy in the muscles into Ke of the bikes by doing work. Okay. So that's the idea behind question number 14.